This is an animation of oscillating pressure gradient pipe flow, where the black color borders represent the pipe and the blue color curve represents the horizontal direction velocity at any x location. The red color bar indicates the pressure on either side. So first we'll animate for the fluid air with a time period of with pressure varying with a time period of approximately 5 seconds. You can see that in the center, there's a region of potential flow, and there are peaks on the side because of the wall's viscosity effects, which try to travel towards the center, but before they can travel, the direction of pressure gradient changes. So if this was a steady Poisson flow, your fluid velocity would be somewhere over here, like this, a much greater velocity curve. Now let's change the fluid to water. Let's do it for a shorter time, but with the same angular frequency and same pressure difference, pressure gradient. So we should expect that there'll be very little fluid velocity. So you can see that the fluid velocity is almost zero because this pressure is not enough to move a higher density fluid. So now we can raise the pressure gradient accordingly, because water is 1,000 times denser. So let's make it 1,000 times. Now we can see that the region of potential flow is larger, as in almost till the edge, the fluid has a uniform velocity all throughout, but only at the edge there are peaks, and the peaks do not travel through here. That is because the kinematic viscosity of water is actually lower than that of air by an order of magnitude. So let's play that with a higher frequency now. So now we have a higher frequency of 1 Hertz with the same pressure. Same. This is still water. Let's play it for longer duration. Now you can see that it oscillates faster and it is moving at a smaller amplitude, as in the velocity's amplitude is smaller now than the previous case, because it does not have enough time to catch up to the pressure gradient. One more thing that we can notice in all this is that the velocity lags the pressure gradient by 90 degrees. So if I just play, say, air, time period of 5, oh, there's too much of a pressure for air. So let's reduce the pressure for air and run. You see that whenever the pressure is higher on the right side, at its maximum on the right side, the velocity is close to 0. So which means that there's a 90 degrees phase lag between the velocity and the pressure gradient. Now let's try the same higher frequency that we tried, but now for a fluid which has a similar density as water, but a higher kinematic viscosity, which is jet fuel. So we saw that for water, the peaks were only close to the wall, very close to the wall, but now the peaks are traveling further inside the diameter of the pipe. This is because of the higher kinematic viscosity of jet fuel.